Physics BN College. As we all know, in recent years, computer simulation and programming finds n numbers of application in different field of physics. It can able to successfully able to replace various experimental setup virtually, as well as it can able to finding a numerical solution of large computer program or computer equation or mathematical equation within a short interval of time. So keeping all these issues in our mind, we are proposed to organize a webinar on this topic, and as a result of that, we have organized today's webinar on physics via computer simulation. To address on this topic, we have invited Dr. Rakesh Maulik as a resource person. Now I simply and briefly like to introduce our resource person, Rakesh Maulik, with you all. I have prepared a short biography on him, so I want to read the note. Dr. Rakesh Maulik is presently working as an assistant professor at Lovely Professional University, Punjab, India. Dr. Maulik is a theoretical physics researcher and physicist. He received his PhD degree from Center of Plasma Physics Institute for Plasma Research, Guwahati, followed by which he did his postdoctorate fellowship at Institute for Plasma Research, Gandhinagar, Ahmedabad. Dr. Maulik takes keen interest in various simulation techniques such as fluid simulation, particle in cell simulation, Monte Carlo simulation, etc. He has published n numbers of articles in the international journal, as well as he published many book chapters. Occasionally, he loves to write popular scientific articles and is passionate about communicating science. So on the behalf of all participants and organizing committee, I would like to welcome our resource person sir to this occasion. Now I would like to request our principal sir, Dr. Dhruva Chakraborty, to formally inaugurate today's webinar. Sir, I switch it over this to you.
Thank you, Neelam. Good morning,
Yes,
everybody.
Sir. Thank you, sir.
Good morning, everybody. Welcome to all of you to this webinar on physics via computer simulation organized by Department of Physics of BN College, Dhubri. Special welcome to all the participants from institutions, universities other than BN College who have joined from different parts of the country. More than 800 persons registered for this webinar, and in addition to Google Meet, this webinar is live on Facebook as well as in our college website. I would specially like to welcome Dr. Rakesh Maulik for according his consent to act as resource person in this particular seminar. A little bit about BN College for those who are not very well known to the college. The college was established in 1946 in the town Dhubri, which is in the western part of Assam, sharing the district shares border with Bangladesh as well as West Bengal, the Kuchbihar district of West Bengal. Since then, at that time, the college was the only college in the western part of Assam, helping the students in pursuing higher education, particularly in science. And the college has come a long way since then. And now we offer science, arts, commerce, computer application, a PG in chemistry, SMEs, etc. So I hope this particular webinar will be helpful for all of us, particularly for the students and teachers of physics, and the interactions and deliberations will be helpful to all. So again, I would like to thank our resource person, Dr. Maulik, for agreeing to our proposal to act as resource person. And I welcome all of you to this particular seminar. Thank you. And I declare this webinar to be open. Thank you.
Thank you, Principal Sir. Now,
Thank you.
before going to our lecture, I request all the participants to mute their microphone and videos so that we can have a great interaction with all. And during the webinar, if somebody has some question, they can put it in the chat box. And after deliberation of lecture, we will go to the question and answer session. So without delaying any time, we are going to the presentation directly. In the presentation, our research person will talk about giving numerical solution of the heat diffusion equation and Laplace equation using finite differential approach. If I am not wrong, he will use Python and MATLAB code for this. Is it sir?
Yes, Neelam?
Yeah. So I handed over this
Yeah.
microphone to our Rakesh sir for continuation of the program. Thank you.
Thank you, Neelam.
Thank you.
Honorable Principal, sir. Honorable Head of the Department of Physics, BN College. Honorable uh, Coordinator, IQSC. Esteemed faculties, dignitaries, and my dear students. So, at the very outset, I'd like to thank the organizers for giving me this opportunity to deliver this talk. So, without any further delay, I'm going directly to my talk. So, hope you will enjoy my talk. So, I hope my screen is visible to everybody. Yeah. So, there's physics via computer simulation. Now, once we talk about computer simulation, this is something a very emerging area of research these days that we have previously used to do. Previously, we used to do some experiment or do some theoretical works like solving differential equation analytically just by hand, or doing just by finding analytical expression for a different set of problems or something like that. But now these days, as we have grown up in physics, we have developed so much of complexities that it is many times it is difficult to find an analytical solution to the problems. So in this whole one slide, you can see there are many different pictures, like suppose how light goes past a car, how it goes past a cylinder, how there is a cyclist who is cycling. In that case, normally in case of races, basically, just 2 seconds or 3 second delay matters a lot for a cyclist, because within just 3 second delay, somebody gets the winning seat, somebody could not win maybe. So in that case, we have to exactly simulate, or we can simulate the flow past the cyclist, or in which position, in which gear he should ride on his cycle, so that he can get some extra edge over the other participants, right? So all these things today in modern world come under this branch called computer simulation. So let us start with my talk outline. Talk outline would be like this. First, we will start with introduction part, what is basically a simulation. Then we will go into problem formulation, like since so that we can have a direct hands-on experience with this topic. That is why I have selected these two equations mainly: heat diffusion equation, Laplace equation, which we shall solve on Python. First, I'll develop the computational technique in brief, how to solve that, and then I will take you to Anaconda platform, and we shall try to solve the problems directly on Python. And then in order to do so, we have to little bit introduce ourselves to finite differencing. What is the meaning of that? I will talk about that. Then I will talk about mathematical approximation of the derivatives. Suppose some derivatives are there, like uh, derivative of temperature field with respect to displacement, or derivative of temperature field with respect to time. How to write that as a difference formula? That we shall introduce. Then finite difference operators, and finally we will write the final expression, that is finite difference formulation of the problem. And later on we will visit the Python programming and results for each problem, right? Well, so moving ahead, what is a computer simulation? Now, simulation and computer simulation are actually two different terms. They are distinguished by a little bit. So, for example, the picture that you can see completely on the right-hand side, there is a person. You can see that this is somewhat space-related issue. So it's called the human in the loop simulation for outer space. Many a times we want to experience. Suppose we want to send an astronaut to the space. Now, beforehand, what we have to do, we have to make him aware of the situation that he's going to face in the outer space. So what we do, we create an artificial space in the sense within the laboratory. We create a space where he can feel the zero G condition, like and zero gravity conditions. And in that conditions, we train him how exactly to work or how exactly he will feel when he will go into the outer space. So there is one more technique, like going on a flight, and the flight sharply goes up and reaches a zero G condition and then sharply comes down, like that. So these type of arrangements, whenever we do, we call it to be a simulator. Say, for example, if somebody wants to simulate, somebody wants to know what happens, what are the things that happens in the solar plasma. So we cannot directly go into the sun and do an experiment. So that's quite difficult, rather impossible. So what we do, we create an artificial environment within the lab with the properties of the plasma may be similar to some extent to that of the solar plasma, and we study all the phenomena that occurs within that laboratory scale, and ultimately we scale it up with the solar plasma. That means in the laboratory we have created a condition which is similar in nature to the solar plasma, say for example, and whatever phenomena that happens over here, so we can study and extract the results out of that, and we can predict that, okay, since this is happening in this laboratory space, so that might also happen in the solar space. And in the second picture, you can see there is a person in the motorcycle simulator. So he is maybe interested in gaming, or maybe interested in taking part of a race, but he's not actually taking part in the race. What he's doing, he is riding on a bike, which is a virtual thing, and he is experiencing, sort of, he's getting the feel over a video game. So that's something we have all experienced in our when we were kids. Like we used to play video games, and we used to experience how exactly, say for example, a biker or a person who is riding on a car, he will feel. So this is also kind of a simulation environment. So where somebody is not actually participating, but sort of is getting the experience virtually. So that's a simulation. Now, coming to the computer simulation is basically the process of mathematical modeling performed on a computer, which is designed to predict the behavior or the outcome of a real world or physical system. Now, there could be situations where we cannot do some experiment. Now, suppose I give you a uh, metallic slab, maybe two-dimensional structure, and I give you the boundary condition. Suppose I say in the I mean, in all the four sides, I have applied some of the some temperature. Like suppose some end I have kept it at 400 degrees centigrade, somewhere at 200, somewhere in 100, and somewhere at zero maybe. And I am interested to know how the temperature gets ultimately eventually distributed all over the space. Now, it's very difficult to know, because what you have to do, if you have to perform an experiment, you have to put some thermometers. It could be digital or analog, whichever it is. You have to put thermometers at regular interval of space. And finally, from by the reading of the thermometer, we will come to a conclusion. Okay, so this is my temperature distribution at every point. Now, suppose similar thing. Suppose you have got a rod, a linear rod. One end of the rod is kept at 100 degree, another end is kept at 0 degree. So I am interested to know what will be the temperature at point, say x. X could be anything. X could be halfway between the rod. It could be 1/4 of the rod. It could be 3/4 of the rod. It could be any point. How would I know what will be the temperature at that particular point? Again, we have to go for a direct measurement. Now, computer simulation is helpful in this aspect. Suppose we have the boundary conditions. We know what are the conditions applied at the end of the rod. Then we have a differential equation for that. We can solve down the differential equation. And for a particular amount of time, we can say, okay, so at this instant of time, this is the temperature at a particular location where I'm interested in. Got it? So here comes mathematical modeling into physics. Now, many a times, now somebody may ask me, like mathematical modeling, I can solve the equations by hand also. Yes, we can, but to what extent? We can solve it to some small extent, like whenever the expressions are a little bit easy, maybe, or that they can be done by hand. Otherwise, for modern day complex problems, we no longer can go into the finding out the analytical expression. So we have to somehow model it into the computer or make the computer understand what is my problem, and computer will give me the result back. So in this particular figure, the third figure, where basically you can see a flow past a solid cylinder. So the white dot over here that you can see, this is nothing but a solid cylinder. I mean, the axis goes into the page of this paper. So a flow is there. It could be airflow. It could be any liquid flow, which is flowing past this solid cylinder. And you can see in the behind backyard of the cylinder, you can see this sort of loops or vortices. We call them technically von Karman vortices. So these are formed, but experimentally it is very difficult to get an idea where the curling of the velocity field will be, how much. These things, these type of questions are very difficult to answer by doing an experiment. So what we do, we perform a computer simulation. Fine, I hope this part is clear. Let's then go forward to the problem formulation so that we can understand this much better. It is always better to do it by hand or solve the problem so that we understand the concept. So I have taken specifically two problems, out of which one I will discuss in detail. That is the first equation, which is called the one-dimensional heat diffusion equation. And the second problem I will show, that is two-dimensional Laplace's equation. Now, for the first equation, the heat diffusion equation, we have a temperature variation with respect to time. It's a partial differential equation minus alpha. Alpha is basically the heat diffusion coefficient, and with nabla square T, that is equal to 0. Now, what is nabla? Nabla is basically the second order space derivative that we have taken for the temperature. Now, since we have only one dimension here, as you can see in the rod, one end of the rod is kept at 100 degrees centigrade, the other end is kept at 0 degrees centigrade. So what we are going to do, we are going to solve this equation on this particular grid, on this particular domain, and see at what amount of time, what is the temperature distribution. So similarly, now suppose I want to convert this problem into a two-dimensional problem. What I have to do, I have to make it a slab. Now in the slab, you can see slab is just 10 units by 6 units. You can choose your units. It could be in SI, it could be in CZs. So one end, the front end basically, that I have kept at 400 degrees centigrade. The bottom end I have kept at 0 degrees centigrade, say, and the side walls that have been kept at 100 degrees centigrade. So under this circumstance, if we solve down the Laplace's equation, in that case, we shall get the steady state temperature distribution at all points on the domain. Now, little bit on steady state. What is meant by steady state? Steady state means whenever I do not have any variation of temperature with respect to time, this particular term goes on. So whenever this particular term goes up, then what I remain with that alpha delta t equal to 0. So ultimately I can write it as delta t equal to 0, which is a Laplace equation. So heat diffusion equation goes into the Laplace equation whenever you reach a steady state. Well, so let's go forward and see how exactly we can solve this down. Now, there is something called discretization. Now, discretization is a very, very important concept whenever you have to apply the numerical simulation, or you have to do the numerical simulation over a continuous domain. Now, in physically what we have, physically all the things are continuous. So for example, if I have to talk about the length of this rod, it starts from one end, say x equal to 0, and goes to the other end, x equal to L, continuously. There is no matter gap. It is not that there some point is there where the matter is jumping from one end to the other end. It's completely continuous. But since it is continuous, then if I have to solve it down, I cannot solve it computationally over this continuous domain, right? Because I have to, in that case, incorporate infinite numbers of points. Because if I assume this one-dimensional rod to be points on only a summation of points. In that case, there are infinite numbers of points that I can imagine onto this rod. So what I do basically, I do not solve my equation on this complete rod. Instead, I solve my equation on discrete points onto this domain. So here you can see this particular grid. This is known as a grid, where this one is the boundary node. Boundary node in the sense this will specify for the end where I have kept at 100 degrees centigrade. Then the n, capital N, which is written over here, that is for the last end. That means the completely end, the other boundary of the rod, which is kept at 0 degrees centigrade. Now, there I know the temperature. So that is why these have been given as red dot, because I know the temperature as 100 on the front node and 0 as the last node. By the way, these are known as nodes also. Wherever I have got these points, no, these are known as nodes. Now, in the middle, my problem is where, as a computational physicist, my problem is to find out the temperature at all these points over time. Means what will be the temperature here whenever we have got 1 second, so maybe 2 seconds, maybe 3 seconds. As we go along time, then how exactly the temperature gets distributed over all these points. Now remember only one thing here, that these points, the difference between any two successive points should be very, very small. Means if I assume this distance to be delta x, then this delta x should be very, very small. So what we have, if I now combine these two figures, I have this. Means I'm not solving my differential equation, partial differential equation rather, onto the complete domain. Rather, I am solving it on certain nodes, which is basically known as a grid. So I'm solving it on a grid. Well, now in order to solve that, there is some part of Taylor series expansion that we have to know, right? Suppose we know the temperature at any location x. Then what will be the temperature at a distance delta x in the forward direction? Forward direction means, suppose this is my ith grid point, then what will be the temperature at the point I plus 1? I may be interested also what will be the temperature at I minus 1. So based upon this, whether from the location I go in the forward direction or I go in the backward direction, these are known as forward differencing scheme or backward differencing scheme. Forget about the backward scheme. Let us first counter the forward differencing scheme. Now, suppose I want to express the temperature at a location delta x away from the ith grid point, then I can expand this as a Taylor series expansion, provided delta x is very, very small, as t of x plus delta x dt upon dx plus delta x square upon factorial 2 d2t upon dx2. Likewise, I have n numbers of terms. Now, out of these n numbers of terms, I will not consider the term greater than the second order term. I will consider the terms only up to the first order. Why? Because I am interested to find out a difference formula for dt dx. Means I want to approximate the first order derivative of temperature over space as a difference formula. So what I can get, suppose I neglect any higher order term starting from the second order term, then I remain with tx plus delta x equal to t of x plus delta x dt dx plus order of 2. This is known as order of 2. Order of 2 means I have dropped down the higher order terms from the second order. So if I now find out dt dx, what I can write, dt dx equal to t of x plus delta x minus of tx whole divided by delta x. So this is basically the finite difference approximation of the first order differential equation, first order difference or first order derivative, that is dt dx. Now since I have done it in the forward direction, means from the point x I have taken it to x plus delta x, hence we call it forward difference scheme. Similarly, if I have to go back, I can write it easily like as a backward formula. So in the backward formula, we write it as this: dt dx equal to t of x minus t of x minus delta x divided by delta x. So for that reason, what I had done, for that reason, I have expanded tx minus delta x as my finite difference scheme, or as a Taylor expansion, right? Since this has been done in the backward direction, we call this a backward difference scheme. Now, For my purpose today, to solve the partial differential equation, I will use neither of them. Why? Because you can see here in both the schemes, I have retained the terms only including delta x. So since it has got a power of 1, we call these schemes to be first order accurate because I have neglected the terms from the second order term. So I have dropped down the second order term onwards. Hence, its accuracy is only up to first order. Now, it is fine if you solve your equation with first order accuracy, but the problem is suppose you increase upon the grid number, suppose all these points, you increase the density of these points, like suppose from 1 to n, I'm assuming here say 10 dots or 10 nodes. If I now go into, suppose I may wish to go to 100 nodes or maybe 1000 nodes, in that case what will happen, this accuracy will come into action, and ultimately my numerical solution that I will get will be faulty. It will not be accurate. So that is why I need to increase upon my accuracy. So I'll go into a second order accurate scheme than the first order accurate scheme. So I will neither use for forward difference scheme nor I shall use backward difference scheme. Rather, I shall go and use a central difference scheme. What is a central difference scheme? Just make a Taylor series expansion x plus delta x and x minus delta x as we had done before. Now we have to do just subtract the second equation, that is t of x minus delta x, from the first, that is t of x plus delta x. If we subtract that, then what will happen? See, automatically two terms get cancelled. This term and this term gets cancelled. This term retains, this term, the second order term, gets cancelled. And we will assume that we will neglect the terms from the third order equation. Now, since we are neglecting from third order equation, so its accuracy becomes n minus 1, that is 3 minus 1, that is 2. So it has got an accuracy which is second order. So it is a little bit accurate over the forward or the backward difference scheme. So if we just go on into finding this dt dx, what I have, dt dx equal to t of x plus delta x minus t of x minus delta x divided by now twice delta x. So what we are going to find, suppose I have to find the temperature over here, ith node, then I will write, I will get the temperature I plus 1th node and the temperature at I minus 1th node. I will take a subtraction and divide it by twice this space, means delta x plus delta x, twice delta x. Okay, so that's how I find the difference, derivative of temperature at this location. Okay, now this is ith node I have just given for a dummy indexing. I can be anything. I can be anything in the sense I can consider this to be ith node. Then I will find the temperature here. Then in the next loop, I will go into this point and call this to be ith node and find the temperature over here. Likewise, I will start from the boundary and I will go to the end boundary and I will find the temperature at all these nodes. And finally, I will join them all and finally club them together to show my results. Things will be more clear whenever we solve our problems, right? Okay. Now, since in my partial differential equation for heat diffusion equations, I have second order equation, not the first order. So I have to approximate the second order derivative of temperature also. How can I approximate that? Just by central differencing. We can approximate it by retaining this second order term. Means previously what we did in this forward, this particular slide, when we were finding out the first order derivative, we subtracted the second equation from the first. Now in this case, we'll sum it up. If we sum it up, what we'll get? We will get tx plus tx equal to twice tx that I have written here. Then if I sum it up, then these two terms get cancelled because they are the same terms, with one with a plus sign, another with a minus sign, and I will retain this second order equation over here, delta x square over factorial 2. So since factorial 2 is equal to 2 and summing it up gives us 2 once again, so 2 gets cancelled, I retain this particular term. So from here I get d2t upon dx equal to t of x plus delta x minus twice t of x plus t of x minus delta x whole divided by delta x square. So my space derivatives are over. I have calculated the space derivatives. There is one more thing, which is the time derivative. Means how can we approximate the first order derivative with respect to time. Now for time we need not to be that much accurate. It is fine that we do it just as a forward difference formula. Somebody, if he wishes, he can go for central differencing for time also, but In time, the accuracy requirement is not that much as in case of space. So whenever we are solving for space dimension, the accuracy involvement is more than the time. So what we have basically, we just approximate it as finite difference formula. Now remember how I am writing it. dt upon dt is equal to capital T I index I. This index which is given as a suffix or subscript, it is for the spatial node. Spatial node means how I was going from one grid point to the other grid point. But n plus 1 and n over here that has been written, they specify for the time nodes. Time node in the sense, this is my temperature somewhere in the future. This is the temperature of the present. So this is the temperature in the ith node in the present time step, and this is the temperature of the ith node in the future. So we want to predict the future always. So we will write all expression as an algebraic expression as in terms of this future time. So whenever I'll write, you will come to know about this more clearly. So this is basically the gridding over time. So this is the spatial gridding. This is the time gridding. So suppose I have got temperature at this point to be T1, T2, T3 like that over nth time. Then in n plus 1 time, this will be like, say, this will be like T1 prime, T2 prime, T3 prime like that. This will be like in n plus 1, n plus 2th time, it will be like T1 prime, double prime, T2 double prime, T3 double prime, like that. Double prime doesn't mean here derivative, it is just another value. So now we have found out all the derivatives we require to solve our equation, the heat diffusion equation. Means we have we have expressed the second order differential as a forward difference formula. We have also expressed the first order time derivative as a forward difference formula, and we have put it all together onto the right hand side. Now since this is forward for first order in time and second order in space, so we have written it as a forward difference in time and central differencing in space. So that is why these type of schemes are known as FTCS scheme, forward in time, central in space. Means the time discretization has been done by forward differential formula, and this partial discretization have been obtained by central differencing formula. Now, I understand for many of you, those were students basically, this could be a little bit a new concept, or maybe some of you are encountering it for the first time. So I understand the level of difficulty involved in understanding or grasping these concepts, but hold on to this. I hope you will understand it as we go ahead, right? Now, what is my next task? That I have found out these differential equations or differential operators rather. Now my next task is to write my first order heat diffusion equation as finite difference formula. Now see the beauty of this technique. The beauty of this technique is that now I am writing it, see, delta t upon delta t, that means the first order derivative of time, I am writing as a difference formula. Then the second order derivative of time with space, I am also writing it as a central difference formula. Alpha remains alpha because this is a constant basically. Now, interestingly, you see, I can write all those, I can take all the term on the right hand side of the equation, and I can retain only this particular term, that is Tj of n plus 1 on the left hand side. Just do not confuse between j and I. Previously, in some point, I have designated these partial nodes to be I. Here I am designating it by j. Just it makes no difference. You can have it any index. Somebody prefer to give k also. Somebody prefer to give j. Somebody prefer to give I. This is just a nomenclature, nothing else. Okay. Somebody likes to write k instead of n over here. Means for time they write k, and for space they write I or j. So it's absolutely a personal choice. But what is important that I am getting here the future temperatures. So this is my temperature in the future, and here is my temperature. Uh, here is my temperature of the present. Means I started with some dummy variables. I will show you when I go to the coding part that we have to start with some dummy variables. Now, dummy variables means you have to initialize the temperature field. Now, what do you mean by the field? Field in the sense, starting from the first node to the last node, you have to assume some value of the temperature on each and every node. You can assume anything. You can assume 0, you can assume anything of your choice. You can assume it to be 1, you can assume it to be 0.5 on every location. It is completely independent. Solution will ultimately converge. But only thing you have to remember that the boundary nodes, wherever you have given the temperature profiles, that you cannot change. On the one boundary, I had 100 degrees centigrade, the steam point. On the other boundary, the last boundary, I had 0 degrees centigrade, that means the ice point. These two must remain fixed. They cannot be changed. You can change your temperature according to your wish, but you cannot arbitrarily left it open. You have to put some value over there. Okay. So whenever we put some value onto the boundary, we call them to be Dirichlet boundary condition. However, there is a point where we do not give boundary condition on the endpoints, rather we rather specify the first order derivative of the temperature field on the boundaries. They are known as the Neumann boundary condition, but that is a little bit difficult. I have a code implemented, but that is not what my scope today. That is, I feel it is beyond the scope. So I'll just go with the Dirichlet boundary condition in today's class. Got it? So what we have now, we have the present temperatures, and based upon the present temperatures, I am kind of predicting the future temperature. So next what we'll do, then I will replace, once first future is predicted, then I will replace all this temperature by this first predicted future. Then I will go to the, based upon those first predicted future, I will go and evaluate the second predicted future. Likewise, I will go on to evaluate this until and unless we reach a steady state condition. The beauty of this equation is that initially we had a partial differential formula. Now I have got an algebraic formula. So I have reduced my partial differential equation to a simple algebraic equation by finite differencing method, right? So that is the beauty of this method. So, well, fine. Now, in order so that we can compare it with some analytical expression, means how would I know that my numerical solution is correct or not? So for that, I have to compare my results with some numerical, some analytical results. Now, in this case, at steady state, what will be the analytical expression? Now, steady state, as already I said, whenever the temperature field doesn't vary with time anymore, in that case, what I can write that delta t, capital T upon delta small t, this part goes off to 0. And I remain with only a Laplace equation, that is delta t equal to 0. So for one-dimensional problem, it is just d2t by dx2 equal to 0. So if I have to find an analytical expression, which is shown in this slide, this is pretty well known. We can solve it down. This is just nothing but a linear equation, straight line equation, t is equal to mx plus c kind of equation that we'll get. But only two different constants are there. One is m, another is c, which are undetermined coefficients. So since we have got two undetermined coefficients, we need two boundary conditions, and we have two boundary conditions. Like at the first node, that is wherever x equal to 0, I have temperature to be 100, and at the final node, the temperature was 0 degrees centigrade. So based upon this, we can find the value of c to be 100, and the value of m, which is the slope, is minus 100 by capital L. Capital L basically the length of the rod, which we can choose of our own. So we have determined the undetermined coefficients m and c, and if we put it down, then I get the analytical expression for the temperature, that t as a function of x equal to minus 100 upon L x plus 100. So if I know all the values of, if you give me the x, suppose
Hello, sorry, sir, you are not audible. Hello, sir, you are not audible.
Hello,
Okay,
Rakesh sir. Hello, Rakesh sir. Hello. Hello, Rakesh sir. Your sound is not coming here. Hello.
yeah. Now am I audible?
yes, sir. Yes,
Okay,
sir.
okay,
Thank you,
okay,
sir.
Okay.
okay.
Thank you, sir.
Somehow it went wrong. I'm so sorry. Okay.
Okay, it's okay.
So how much you missed? How much you missed?
For last 1 minute, I think.
Oh, okay. I'll just go back and once again I'll do that. Okay. Just give me a
Please,
hint.
please,
Just
please project your screen again. Yeah, it's presenting. Yeah.
yeah. Now is it fine?
Yeah, yeah.
Okay,
And
this slide.
participant, you are requested to pin the presentation so that you are without interrupting, you can see the presentation. So pin the presentation, not the video. It's okay.
Yeah. So,
Yes, Rakesh, sir.
could you hear this particular slide?
Yes, sir. Yes, sir.
Yes,
You are
yes.
audible and we can see also.
Okay, okay.
Yeah, you have started. Yeah.
Well, fine. So what I told right now, just that I am trying to find out an analytical expression so that I can compare with my numerical. So what was the analytical expression? By just solving the Laplace equation, I could find out the analytical expression as t as a function of x, that is equal to minus 100 upon L x plus 100. That is basically I'm getting a negative slope. This is just like a just a straight line equation. Now, just before we go into the numerical solution, let me give you a brief hint of the algorithm that I'm going to follow. So the first task when we solve down in Python. Now, Python is very interesting. Python is a freeware basically. It's a free software tool for data analysis as well as coding. Any other software tool like C++, coding platform, Fortran, we can solve. But Python is quite handy in a sense that you need not to define this variable. Otherwise, if you go back to Fortran or C++, you have to define every variable, like whether it is an integer variable we were talking about, whether you are talking about a real variable, all these things you need to define. But in Python, things are taken care of by default. So we need not to bother ourselves with what we have to define, whether we have put a semicolon at the end of a statement. All these things are completely, they bother us. So that is why it is very easy. There is one more analog to Python that is called MATLAB. But the difficulty with MATLAB is that MATLAB is not a free software. This is basically a paid software, and it's a little bit pricey. So that is the reason why people across the globe now prefer Python over any other language for many of the calculations. Like this is the time that we are running through this pandemic COVID, and many a times you must have come across this simulation where we predict where can we predict, how can we flatten the graph, all these questions that comes pops up to our mind. All these things are normally solved over Python. All the graphs that you have seen, they are also actually the result of Python. So in this particular case, how can we implement that? First of all, we have to import the Python library. The name is mentioned over here. Import the Python libraries. I will show you how exactly what are the libraries required for us. Then define the domain parameters, initialize the temperature field, and start the time loop. That's it. These are the 4 points that you have to remember in order to solve this partial differential equation or heat diffusion equation. In the loop, which is time loop, what we do like for all new values, we calculate the new temperature field. Means you initially had a temperature field which you initialized to be 0 or to be 1 or to be 0.5 at every nodes, as I told you earlier also. This is a completely up to yours. How do you initialize your temperature? Then from that initialization, that is an error because you initialized it as incorrect field, right? Now, as you go upon time, you gradually go to the original solution, means accurate solution. So what we do, we start with erroneous solution. As we go over time, then we correct ourselves. Correct ourselves based on our past experiences. This is quite like our human life. We started whenever we were kids, we used to do many mistakes. Then as we grow up with time, we learn that, okay, this is my mistake, this I shouldn't do. Then this is the corrected version that I should do. So likewise here also computationally, we start with an erroneous solution or we start with an erroneous temperature field. And over time, as we go on, we rectify that errors further and further and further, and go into the ultimate solution. So there will be a time when my numerical solution will completely match with the analytical solution, and I will stop my time loop over there, and I will say, okay, uh, this is basically the solution. Now you can ask, here it is fine. You are on the safe side that you have got an analytical expression. What about where I do not have an analytical expression? Because if I can find an analytical expression, what is the need of finding a numerical task? Yes. Now, in order to do that, we have to go for error. So second step is calculate the error. How much error you calculate, how much error uh, you incur while you solve down your equation. You have to trace it. You have to make a note of that. This error should gradually go up to zero. Now, what is zero actually? There is nothing called zero because we can computationally, there is nothing called zero. Computationally, zero means it could be 0.001, it could be 0.0001, it could be like that. So, technically, we stop ourselves. Technically, we stop ourselves whenever we reach an error level of 10 to the power minus 6, and we say that fine, now we have reached a sufficient error level, sufficient minimized level of error, and this could be considered as a correct value of my temperature. Fine. Then replace the old temperature profile by new one and finally plot the results. So this is my algorithm that I'm going to solve. So let's go forward to the Python programming. So here is the code. Now in the code, I have, based upon those algorithm points, 1, 2, 3, 4, I have marked them as 1, 2, 3, 4 over the slide. I guess after this particular session is over, anybody is interested to obtain these slides, I have no problem to share them at all. Uh, so import the libraries, the first point was there. So import the libraries in Python, all the data analysis part, like all the array in the sense, all the temperature profile that you have to put it as an array. Array means sort of a matrix that you have to build by NumPy. So import, you have to call the NumPy library. So import NumPy as NP. You can write this NP as anything. You can write your name also, no problem. But technically, it's a standard point that everybody writes it NP. So I'm also writing it as an NP. Then you have got import from math, import star. Star means the product basically, so that you have to import from math library. Then import matplotlib. Matplotlib is the version of Python which helps us in plotting our results. Then you have to show the notes plots in your notebook. So that is why we use this matplotlib.use nbag, and finally import matplotlib.pyplot as plt. And matplotlib import grid space. All these things are a little bit technical things. I will explain as I go into the code. Now, second important, most important part is the simulation parameters. Simulation parameter means where you have to define your domain. Now, this is my domain, Xmax. Xmax means the length of the rod. That I have defined it to be 10. Now, it could be anything. It could, you can consider it to be 10 meters also. Like, it depends upon what is the unit you have used for temperature and the alpha. Alpha means the diffusion coefficient. If you have used alpha as a SI, then this will be an SI. If you use that in CCS, then that will be a CCS. That is the only thing you have to know. But here I am not concerned with my system of unit. I'm just concerned with some values, so that because our main motive is to understand how it works. Then n is equal to 50. N is equal to 50 means I have considered, remember those points I created as a grid points? I have considered between the boundaries 50 grid points. So I have used 50 nodes or 50 such definite points to solve my equations. If you use more numbers, your solution will be even more accurate. So that is the thing. But there is a limit to that. I mean, after some time, how far you increase the number of node, depending upon that, the error further doesn't get reduced. So suppose you use only 5, error will be more. You use 10, error will be little minimized. You use 50, error will be little minimized. Then if you go into n equal to 100, error will be further minimized. But there will be a value of n beyond which there will be no minimization of error. So that's quite fine. Then dx means the distance between any two successive nodes. That should be like x max divided by n minus 1. And dt is the temperature times time step. Basically, time step I have considered 0.01 second. These are all based upon your choice. Then alpha, which I have written it as ALP, that I have considered as a dummy variable, just 0.5. You can check it for yourself. We can consider any real arbitrary, real values also. So, for example, you consider alpha for copper or for iron, like that. Now we initialize the time to be 0 and x means my domain to be np.linspace 0xmax1. Now what it does, it distributes the 0 to xmax. It creates n points, n equispace points between 0 to xmax. So it will create 50 equispace points between 0 to xmax, which is the endpoint of my rod. Got it? Now comes the main part of the Python scripting. So this part and this part, the following part maybe, these basically, these two I will explain as I go into my Python programming. So let us go into the Anaconda platform. So here is the Anaconda platform. Anaconda, if you install, you will get something like this Anaconda Navigator. From where there are many things. See, there is Jupyter Lab, then Jupyter Notebook. I will be using this Jupyter Notebook. Then you have got IPython console, then Spider, where you can write your Python codes. For if you have a long Python code, maybe, then we prefer to write it on Spider. Then Glue, Orange, these things are also for solving Python programming. But for my purpose, I'll suffice using this Jupyter Notebook. So if I open it up Jupyter Notebook, the one beauty is that I can run my simulation on browser. See, this is basically the Mozilla Firefox browser. On this browser, I'm running my code. Can you believe this? So just to do numerical simulation, you just need a browser and your just Jupyter Notebook. That's it. So you can download this Anaconda from, this is freeware. You can just type Anaconda download in Google, and you will get little bit size is a little bit higher. Like I get 600 to 700 MB. It will be like. So if you download it and install it, very easy to install over Windows. You can start your numerical program, right? So once I solve it down, see here, another beauty is that you can, in this notebook, you can write it as a LaTeX format. See, all these equations I have written as LaTeX. So if I just double click it, you see how I have written it. I have written it like this. All these are like LaTeX format. So once you put it over here and just press enter, you get this, right? And similarly for all other, shift enter, and here to shift enter. And you get all these equations nicely written. This gives you a reference also what you are solving for, right? Now, all these two things I have explained. Now I'm going to explain this part. See, plot the temperature profile. So what I told that we have to first generate, or we have to first initialize my temperature field. So in that field, I start it with zeros. np dot zeros n means it will create 50 points, all of zeros. Got it? It will create
Rakesh
only 50
sir,
zeros. Yes, yes.
Rakesh sir, can you zoom
Yes,
it
yes.
you? Okay.
Yeah, I
Yeah.
can zoom it. I can zoom it. Is it fine now?
Yeah. It is fine now, I think.
Okay, fine. Okay. So here I have created a temperature called T and something called temperature T new. T new means the new temperature that I am going to get over time step, and I will replace the T new by this old temperature T. And these are my boundaries. See, I have considered T new 0. 0 means the first node. In Python programming, what we have, the first node, I do not write it as 1. The counting starts from 0. So that is why the last node will not be n. It will be n minus 1. Because since the counting starts from 0, so the last will be n minus 1. So that is something you have to remember. Otherwise, in MATLAB or Fortran, the counting style is not like that. In MATLAB or Fortran, the counting starts from 1. If you're talking about the first node, then you have to write t new 1 to be equal to 100 and t new n to be equal to 0. But in Python, since the counting starts with 0, I'm going to write it as t new 0 to be equal to 100 and t new n minus 1 to be equal to 0. Now, these are my fixed points. In between, I have all the values to be 0. So that's an erroneous solution. So I started my temperature with an erroneous solution. Now let's see what is my analytical expression. This is my analytical expression that I have created so that I can compare. And finally, I have got the plotting part. Now see, this may look a little bizarre to you, but this is a very nice thing in Python, that you can create an interactive plot. Interactive plot in the sense, you can stop your plot whenever you want. You can start with once again like that. So plot.in bracket. This is basically for creating an interactive plot. Then yeah, this is a technical style of writing in Python. Fig1 is equal to plot.figure. This is basically figure size will be 8 by 4. In the browser, it will reserve a space of the order of 8 by 4. It has got its own unit. Then GS1 equal to grid space. Grid space means grid specification dot grid spec. 1 to 1 to in the sense this will create two figures with one row and two columns. This will be very clear to you as you see the plots. Then width ratios will be equal for both the plots. Then height space will be 0.3, width space will be 0.3. These are also technically values. You can play around with this code once I share it with you. And you can just change these numerical values and see how exactly Based upon these values, things change. These are just nothing but, I mean, these are just your uh, plotting profiles. Now in Python, always you have to create something called axis. So I create a variable, axis variable called x1, and I create a plot, subplot basically, zeroth subplot. That means the first subplot. In the first subplot, I'm going to plot the temperature profile, T new, with x versus temperature I'm going to plot. And see, I have given a comma over here. Why? Because first it will start with a value which is the erroneous value, and gradually as we go on improving the value or improving upon the solution, this comma will take care of the new variables. New variables means this t new will gradually modify, so that will be automatically taken care of. So similarly, in the second plot, I plot it for the numerical error, the difference between the numerical temperature T and the analytical temperature TA. So that I'm going to plot it as a black curve. The color of the cloud will be black. Here it will be red. Got it? Now, once I come to the loop over time, so I have run it for, I'm going to run it for 15,000 times. Now see over here, for I in the range 1 to n minus 1, means for all the nodes within, because boundary nodes were clear. The zeroth node was 100, temperature value was 100, and for the last node, temperature value was 0. But what about in between? In between, we have to rectify it because it is no longer 0. So how do we rectify? We put this particular expression. Now, what is this expression? This expression is nothing but the expression that I got as this particular expression, tjn plus 1 is equal to alpha delta t, all these things that I have written over here. This is nothing but I'm going to write it here, this particular line. Got it? Then I am going to write, calculate the RMS value of the error. I hope this is pretty clear. You can understand it by watching it. And then see, I'm replacing the temperatures. Like this is the old temperature. I'm replacing it by the new temperature. So whenever it will come to the next step, means 1500, suppose it starts with 0 in the loop. Then it started t values to be all zeros, and it calculated a t new. Then for the next loop, I replaced all these values of t new to t. Then whenever I will run it for the second loop, then all this temperature will be based upon the t new, which was calculated in the previous time step. So those who are a little bit new to this kind of programming, you have to little go and dig it by yourself what I mean. Okay, things are otherwise very simple. If you just sit with it for a little amount of time, then you can easily understand that. And finally, I plot my results. Basically, I do not plot, I update those values. See, I have given here t1.set y data, t new means I am replacing those plot data to be t new and say y data to be this for the second plot. And finally, I want to save this. So I'll just mark it as comment because I do not want to save this file right now. I already have saved it. Now, if I do that, what I get, just let's run this code and see what I get. So you have to go to cell, run all. See over here, this red was the erroneous solution and the green was the analytical solution. As we are going over time, they are getting matched together. The solutions are getting matched together completely. Okay, I'll run it once again for you. Just let it finish. I'll write it once again for you. It will run up to 15,000 time steps, out of which it is now 11,000 only. See, there is no difference. This was the error, RMS error. Now, what is the RMS error? I have brought it down to 0.009. You can, if you run it for further time steps, since I have run it for 15,000 only because of the time limitation. Otherwise, you'll have to wait for long. So that is why I'm running it for 15,000. Otherwise, if you give more, like 30,000, 50,000 time steps, if you run, this error value will even come down to further, right? So I'm running it once again for those who couldn't see it nicely. You will see that the red curve, which is my numerical solution, will gradually approach the analytical solution, which is given by this green line. And that's what is a predictability. That is what is showing that over time I'm gradually approaching a steady state. Steady state means where the temperature doesn't vary further, because whenever it matches with this straight line curve, see, there is no further variation. It doesn't go up here and there, it doesn't fluctuate, it doesn't oscillate, right? So, well, fine, I'm running it once again. Now see, the first node was 100 degrees centigrade, so it is showing 100. The last node was 0 degrees centigrade, it is showing 0. So what is the temperature in between? Now you can say, suppose at 4, x equal to 4 meters, so for example, if I consider it to be SI system, then x equal to 4 meter, what is the temperature? Go ahead, 60 degrees centigrade. At, say, for example, 6 meter, what is the temperature? It's 40 degrees centigrade. At x equal to 8, what is the temperature? It's 20 degrees centigrade. So like that, you can find out the complete distribution of the temperature. Now, this is all about the numerical profile. Now, what about the error? Once again, I'm running it, C. That's great, yeah. Now, see here, the error is going down. Initially, we had error. But as the solution is approaching the analytical expression, or steady state rather, this error is getting 0, 0, and close towards 0, and ultimately it will come down to a very, very low number, almost about to be 0. Okay, so do you see that? Yeah, see, there is no error remaining now. So you can further bring down the error by improving this, just by increasing this time step. Fine. So that's about the one-dimensional solution. So these are the plots basically that I have taken. So I mean, these are just for time step 0, then time step 40, then 80, and ultimately 100. Just 4 snapshots I have shown you. And these are the alpha values. There has been, this data have been taken from Wikipedia, the source as already I have mentioned. You can now test for yourself by giving the real values of alpha. However, these values have been given for millimeter square per second. So if you want to do it for SI system, then you have to convert the millimeter into meter. So you can give a real value of alpha into the code and compare the time required to achieve the steady state for 2 different metals. So for example, you want to compare between copper and gold. You want to compare between copper and aluminum, or copper and steel, or copper and iron. So you can do that by yourself. The code remains the same. Just you have to change the value of alpha. You may have to change the time step values, which I gave 15,000. You may have to increase or decrease a bit, depending upon the alpha. If alpha increases, the diffusion will be fast. The the solution will converge very fast. Means it will reach the steady state fast. Got it? Fine. So up to this, it was one-dimensional problem. What about two-dimension? As we go up to two-dimension, here, now this is the two-dimensional Laplace equation. In fact, this is the last problem that I'm going to discuss in brief. Now in two-dimension, as I told that the front edge, I had got this to be 400 degrees centigrade. So for example, the bottom one at 0 degrees centigrade, the side walls are kept at 100 degrees centigrade. So then we, at steady state, means here I'm not going for any time evolution. I want to know the steady state temperature, means what will be my temperature at steady state whenever there is no variation with time. Now, since this is a 2D plot, you will not get a graph, you will get a contour result, right? You will get a colorful graph. So, but at the very beginning, what you have to write, you have to bring down this partial differential derivatives as a finite difference formula. So as already I know how to write a finite difference formula for second order derivative. So that's what I have written over here. Now, suppose for my own problem, just I assume that dx equal to dy. Dx dy means, suppose you form a grading over here, then this distance between 2 nodes in the x direction is dx, between 2 nodes in the y direction is dy. If I assume them to be same, that means having only one value, say h. In that case, what I can do, I can take dx dy common from here, and I can take it down to the other side of the equation, and that will be 0. So if I now just write Tij from here, Tij means at any grid point I along x and j. Now see here, It is quite unlike the previous problem. In previous problem, I used only one index, I or j. Here I'm using both, ij. Why? Because this time I have got two-dimensional problem. So I have one index I for x direction, another index j for y direction. So if I have to say the temperature at any point, I have to give it both x coordinate and the y coordinates. So that is why I'm indexing it as ij. So if you just mathematically manipulate it a little bit, just one or two steps, in that case you can get that Tij equal to 1/4 Ti plus 1j plus Ti minus 1j plus Tij plus 1 plus Tij minus 1. So at this particular node here, if you want to get the temperature, so this is basically the which was done on this continuous profile. So suppose you want to find the temperature on any grid point. How would you find? It depends upon it is basically the average of the temperature of the near neighbor nodes. Near neighbor node means the eastern point, northern point, western point, and the southern point. So it depends upon the temperature on all these 4 points. Got it? So this is basically the code. Once again, this is quite alike the code that I have recently explained. You have to first import the libraries, then define your domains. Then you have to go for, in the third position, that plot this. And in the fourth, you have to go for the looping part. This is the front part of the looping. This is the error calculation. And this is basically the boundary condition that I have. This is quite self-explanatory. You will understand by yourself only. And here is my temperature field. Now let's see if we go back to the solution, how exactly this can be written. So this is basically the initial description that I have given here. This is a Jupyter notebook. Here is the code. This code is a little bit longer than the previous one. Let me run it once, say for example, so that you understand. So run it. See, I'm plotting the graphs at each 50 degree, at 50 interval of time step. And I have given it as an instruction that if error goes below 10 to the power minus 3, you should stop running the simulation. This instruction has been already given to the code. So if this error comes down to 0.001, it will automatically be stopped. Now see, this is basically the node, or this is basically the line where I kept temperature to be 400 degrees centigrade. Here I kept it as 100 degrees centigrade. Here I kept it 100, and below I have kept it to be 0. So how exactly, with respect to iteration steps, the error is being minimized, and as the error goes down, you rest assure your solution is converging. What do you mean by solution is converging? Solution is converging means your solution, or which is the numerical solution, it is gradually approaching the true solution, analytical solution. But since you do not have an analytical expression in this case, you just track this error. If this error goes up below a certain level, you say that, okay, now I am satisfied because my error has been minimized. So I believe this is my ultimate thing. So here is the plot that you can see. So error goes below, like 0.001020. This is my error. You can give instruction like for further minimization of the errors. And in just 1350 time steps, this has converged. The solutions have converged. Now, one thing I would like to explain here, this particular part. So this is the instruction that if error is less than EPS. EPS means, see, I have defined here. Here, EPS has been defined to be 10 to the power minus 3. So if error goes below 10 to the power minus 3, which is below or equal, in that case, you stop. Break. Break means it will come out of the loop. So only one thing you have to note, that here I am, since this is a two-dimensional plot, if you just give like ax dot plot, it will not plot. For that, you have to go like imshow, means image show. This is basically an image processing tool for this particular part, for showing this contour plot. People can also write it as contour plot, like plot plt or ax dot contour x, y, and ultimately temperature. That is also fine, but the plot is not so beautiful as it happens in this case. So normally I have seen in my experience of Python that whenever we plot like two-dimensional contour plots, we plot it as a IMShow, right? Now see here, IMShow, what I have written, T dot T. Now the first T is my temperature, second T is basically a transpose. Now whenever you incorporate a 2D data, uh, the result that Python gives you is basically is a transpose matrix. Means if you have to see it in accordance to you, means I know that this is my top boundary, this is bottom boundary, these are the side walls. If I want to visualize this in this fashion, then I have to take a transpose of the matrix, because whatever Python gives me, whatever matrix Python gives me, that is basically transposed to this matrix. So if I retranspose it, I will get this particular thing in this fashion. Now this is a visually correct because I know my mind knows that, okay, this is my front edge, this is my lowest edge, these are the side edges. So that is why I have to transpose the matrix which I receive as a result from the Python and plot it. So that is why it has been written as T dot T. Got it? Rest of the things are very clear or self-explanatory. Once you go through this, you can understand by yourself. Yeah, fine, there is nothing. These are basically the errors that I have printed it up. First, initially you see the error was 1, and gradually as you go on, the error is gradually getting minimized. So here you see a plot, error plot. Now this particular part I will just a little bit minimize. Sorry. Yeah, see over here, this black line gives you the theoretical error, and the red line gives you the how error falls as you increase in time step. See, it is almost an exponential fall with time step. So initially, whenever you had a 0 time step or 1 time step, error was very high. It is of the order of 1. But as you gradually go towards increasing your time step, we know that in 1350 our solution converged. So as you go along, the error has fallen to 0. See, and how it has fallen to 0, almost like an exponential fall. Got it? So this is yet again another important thing that you need to track, the errors basically, because otherwise you will not know to what extent of time you have to run your simulation. Because I could have arbitrarily run up to 100, but am I sure that if I run it up to 100, my solution is correct? No, because why? Because error has not been minimized to 0. Error is too much. So for minimizing it to 0, I need to go up to further time steps. So these are the time steps basically, or how error actually falls with time steps. So, right. So that's all basically. This is basically the things. These are the parts of the coding, same coding, and I have used. This is basically the color map jet, the color that you have seen. I've used the jet color map. There are other color maps too, like gist earth, virides, or greens, that will have their own implications. You can try it for yourself or play around with this code. Fine. So this is basically the result that we got for 0, 100, 500, and 1000 time step, right? And this is known as the color bar. The color bar shows, see, wherever this color is this, it is 400. So where do you get this color? You get this color over here on the extreme edge. So that is 400. Then below you have got 0. The side was somewhere here. It is near about 100 here. So if somebody asks what is the temperature over here, it is nearly yellow region. So I can say that, okay, it is somewhere around 250 degrees centigrade. So I didn't know anything within this bar. I just had the temperature known on the boundaries. Now I know the temperature in the whole region. All right. So that's the beauty of numerical programming or numerical simulation. Well, so I am almost toward the end of my presentation. So in conclusion, I would like to say numerical simulation is an important aspect of modern day science and is gradually gaining popularity in almost every branch of science. Maybe biology, chemistry, physics, mathematics, applied physics, wherever, engineering. Now, these days, if you go into research, you will see that we have more and more of numerical techniques are getting developed each day and being used also in each day. Got it? So numerical simulation is of course problem dependent, and based upon the problem, we have various techniques like it could be fluid simulation, could be Monte Carlo simulation, molecular dynamics simulation, particle insert simulation, lattice Boltzmann simulation. There are all sorts of simulation techniques depending upon various problems. And of course, in this particular slide or to today's presentation, I could not discuss. Basically, there are many things that I could not discuss. So there are many aspects which are a little bit like implementing a complicated boundary condition. Complicated boundary condition means implementing a Norman boundary condition or a mixed type of boundary condition like Norman plus Dirichlet. Whatever we have done today is a Dirichlet boundary condition, means the real values of the temperature were given on the boundary. So these type of boundary conditions are known as Dirichlet boundary condition, but you may have a mixed type of boundary condition. Then you have got a flexible gridding. Now all the grid sizes I have considered it to be constant, right? Dx equal to, I have taken a value, but dx may not be equal to 0. It may vary from one point to another point. Suppose you started with dx to be 0.1, and you can have dx goes off as exponentially or goes off like anything. Dx itself becomes a function of something. That is called flexible grading. Then we didn't discussed about finite volume method, finite element method. We rather talked about very elementary technique that is called finite difference method. But you will otherwise know that if you go into higher levels of more complex problems, finite difference method gives you more errors, which is called numerical diffusion. So these are not discussed because they were out of the scope for today's discussion. And lastly, the open source platforms are preferred for simulation these days, like coding platforms such as Fortran, C++, Python. And many a times it is my personal experience with researchers that people like to write codes in C or C++ or Fortran platform, and rather they analyze the result in Python many a times, because Python is a little bit slow as compared to C, C++, or Fortran, as I have experienced it, right? So that's it. These are basically the references, three references I would like you to follow. The first one you have recently come across. This is very interesting book. I found it out. Second one is a very popular book instead by Bala Goswami. The third one is where you will get a detail of these finite differencing techniques. It's called Technique for Fluid Dynamics by C.H. Fletcher. Basically, this is volume one. There are two volumes, volumes one and volume two. And so thank you all for your kind cooperation, kind attendance and participation to this. And I once again like to thank the organizers for giving me this opportunity. And I would like to leave you with this beautiful quote from Rene Descartes. Thank you so much.
Thank you, sir. Now the session is open for question and answer. And before that, lots of queries are there regarding this feedback link. We will made it available at 12 a.m. today, and it will be live for 24 hours. Due to some technical problem, we are not able to post the link at this time. Feedback link we are not able to post in this webinar, so it will be available by 12 a.m. So we are now invite
Okay,
some questions.
I'll just
Yeah,
some people already have given some queries in the chat box. Let me just open it up.
yeah. You can.
Um, just a second. Just a second. Yeah, yes, loading. Yeah, somebody just I saw it went as a flicker in front of my eye. Somebody just say that, can I use it for physics teaching? Yes, of course you can. I mean, once these things are over, I guess the organizers can share the slides and the codes from where you can download it.
Yes, we
Then
can.
there is a question. Yeah. Then there's a question like, sir, can we use Python to simulate electronic circuit? If yes, please explain how can we. Electronic circuit, I believe you can simulate, but I think you better go to, there are more advanced softwares like Simulink, which is a software of Python, software of MATLAB. But normally we do not, I don't know, maybe if there is some tool in the modern day. I don't have much experience with simulating electronic circuit, but yes, one thing I can say, many times we try to find out like nonlinear dynamic analysis of electronic circuit. Many times we want to find like chaos, in which case we solve a couple differential equations, first order, second order, whatever be the case. Then those algorithms we can write it in Python and solve out the circuit equations, like finding the voltage or current profiles like that. But if you want to simulate the complete circuit, like suppose I design a circuit, give a voltage at one point, take out the output from the other, I do not think this is possible in Python because I have not encountered it. Uh, Next,
And here is one question, Rakesh sir.
yes, please.
Here is one question from Doni Jigdum. I have a doubt
Yes.
regarding the matrix, sir. Sir
Yeah.
was talking about transport matrix. Can you please
Hmm.
explain it once?
Oh, yes. See, I'll just show you over here. Just a second. Present now. Just look at this. Uh, Let me see if I can write it here. See over here. Print. Okay. Okay. Fine. This is very large matrix, so you cannot see it. I'm just minimizing this. Um, Say I'm using 5 by 5 grid, and fine, I've used it. And boundary conditions. Okay, just wait. Yeah. Now, Johnny, can you see over here? I have printed the temperature profile. Now you can see the temperature profile. You know that in the boundary nodes, what you had 400 on the top boundary, right? Then 100 on the side walls, 100 on the side walls, and 0 on the bottom boundary. Now see the matrix profile. How is it printed? 400 has been plotted on the right side. Now I know that this right side is not my right boundary. Right side is rather the top boundary. So if you just visualize it as it is, say for example, if I plot it, if I plot it in this fashion, uh, just a second. Yeah, if I do not take a transpose of the matrix and rather I plot it as it is, what I'm going to get? Let us encounter this problem in this fashion. That will be nice. Yeah, in that sense, you see, this is the top boundary. So you are sort of visualizing the matrix in a tilted way, you know. So sort of you have to rotate it. So since we have to rotate it, because we know visually that this is my top boundary, but Python itself, it prints the matrix in such a way that this happens to be the top side. So that is why, in order so that we can visualize in our own frame, we are taking a transpose of this matrix just for the visualization purpose. That's it. It is because of the data entry. The data is entered into the Python in this particular fashion, so that the top line is printed in this fashion. You see? I hope this is clear.
Then Rakesh sir, Krishna Veni is asking,
Yes.
can we use other programming language for simulation? If so, which language?
Yes, sure. This is, in fact, for me, if you ask me for the first time, I'm doing it for Python, this particular thing. Otherwise, previous to that, you can solve it down equally in MATLAB or C++ or Fortran or any other standard language. Normally, for scientific calculations, we use Fortran. We used to do Fortran programming previously, but in modern day, I have seen to use C and C++ more, rather C++ more over any other programming language. So it is better that I would suggest, if you have make a practice of C++, you can easily solve this thing over other languages. It's not language specific problem. Language is of your choice. You can solve it and plot these profiles. You will get the same result irrespective of the language. Yes, of course.
Then Vishal Bharaddas want to know about
Hmm.
better software for analysis of problem with Python language. Suggest a
Mm,
better software for
hmm.
analysis of problem with Python language.
I didn't get this question because you can analyze this problem, in fact, in Python itself. If you are asking about an alternate software to Python, in that case, I can suggest like MATLAB. which is a paid software. Otherwise, in modern day, Python is considered the best for data analysis. Means if you have a large data or any data that you want to plot or do some manipulation with the data, it's better that you go for Python because this is free. Otherwise, MATLAB is there, or Scilab is another software, which is a free version, quite alike MATLAB. But Scilab, I feel its plotting things are not very good. Means if you plot like contour plots or something, the outcome is not as satisfactory as Python. That's completely my personal view. But otherwise, you can use, of course, for freeware, you can use Scilab, or for paid software, is MATLAB.
Then one query is there, if
Hmm.
Python can be used for astrophysical modeling.
Hmm. Yes. We do use Python for astrophysical modeling. Rather, I would like to state in this case that those who are into astronomy, those who receive data, large data from satellites or something like that, they really use Python. I have one colleague who is a doctorate from this IUCA, and someone from IIA. They really use Python heavily. I have seen them to use that for their data analysis purpose. Yes, I don't know whether what kind of modeling they do. I do not have much experience of that, but yes, they do use. So far as I know.
Then there are lots of question. One question is there. Sir, the example discussed where a stable system whereby implementing grids we can solve the problem rather using laborious calculation. Is
Hmm.
it possible in case of unstable or chaotic system?
Yes, of course. This is very nice question, brother. Yes, of course. I had to maybe talk on this. For a chaotic system, such as, for example, somebody is hunting turbulence in a system. Suppose you have got a Reynolds number. You are solving down a fluid problem basically. And if you go up the Reynolds number of a fluid, say more than like 10,000 or 15,000, in that case, you will encounter turbulence into the flow. Or maybe, for example, if you are hunting for a chaotic system, like you are solving for Lorentz equations, just quite renowned equations, Lorentz attractors. Those problems are equally solved, or Python is capable of handling this. But you have to know the technique. Means there are definite techniques. The book that I have given in the reference, the first book basically, that deals up with how to solve the ordinary differential equations, both coupled and higher order differential equations by using Python, and also C++ to some extent. That has been given as a reference. So please do follow that book. Yes, it is quite doable, quite doable.
So there are lots of questions, but our time is very short. So I think those who have some question, they can mail to you, sir. If
Yes,
you
sure.
can
Yes,
share your email ID.
my email ID is simple. It is just rakesh.maulik, rakesh dot mou. I'm just writing it here in the chat box. I'm giving my mail ID,
Yeah,
rakesh dot
and then
moulik the rate gmail.com. Just introduce yourself and put me a mail regarding any query that you have. I would try to resolve it so far as possible.
And regarding the feedback link, lots of queries are there.
Mm.
And we would like to inform you that the feedback link will be available from 12 a.m. That is midnight of today. And it will be live for 24 hours. And it will be available on our college website. And we also think to send the mail to your email, register email. So after discussing that, we will send, if there is provision for sending the mail to your email ID, then we will send to email ID also. But it will be available on our college website. So
Nilam,
without, yes, ma'am.
Nilam, Nilam, sorry to
Yes, ma'am.
interrupt you. Yes, it is possible. We will send the feedback link to their registered mail ID also at the same time. And it will also be available in our college website. So both the participants can use both the option. Hello? Hello? Am I audible?
Yeah, you are audible. I guess
Yes,
Neelam
yes,
Sharma.
yes. Okay, Nilam. Nilam, please continue. Nilam.
Susmita, perhaps he is
Yes.
disconnected. Perhaps he is disconnected
Oh, maybe,
by
maybe.
his low network.
Okay, then, sir, please, sir, HOD, sir,
Yeah, yeah.
sir, please carry forward then, sir, if there is any more questions or whatever, maybe. Or we
Yeah,
can.
I think there is no question at all. Nilam has completed all the questions. And at the last, from the organizing committee, I want to offer my vote of thanks. Okay, Susmita?
Yes, sir.
So at first, I would like to offer my heartfelt thanks to the principal, BN College Dhubri, Dr. Dhruva Sarkavarti, for giving us the opportunity for arranging such a seminar. Next, I offer my heartfelt thanks to the resource person, Dr. Rakesh Maulik, for his nice and lucid presentation, which will definitely help the participants. And next, I want to thank the coordinator of IQAC, Dr. Susmita Sengupta of BN College Dhubri, for their technical support. I must also appreciate our colleague, Professor Nilam Jyoti Datta, who has taken great responsibility for doing his duty as coordinator of this national webinar. I must thanks all the participants from the different parts of the country, as well as my departmental colleagues and my dear students. Again, I want to thank Dr. Rakesh Maulik for his nice presentation. Thank you. Thanks to all.
Thank you so much, everyone.
So, okay, thank you, sir. Thank you very much. It was really a very nice, one wonderful presentation. Lots of things are there, and I think all the participants really enjoy a lot. I again repeat, dear participants, that the feedback link will be available both in our college website, which is already given to you, and it will be also given to your registered email ID. Please notice it will be active for 24 hours. So today at night 12 o'clock to tomorrow's 12 o'clock. So please response and the auto generated e-certificate, receive the auto generated e-certificate. So thank you once again, sir, on behalf of IQ.
Thank you so much, ma'am. Thank you so much.
It's my privilege that this is our first webinar.
This is my pleasure.
Yes, sir, and
Thanks.
I hope that we will meet once again, maybe
Yes,
physics.
sure. Maybe physics
After
with
this
some more problems, like maybe could
Yeah,
could be
yeah.
problems on waves or many other things. There are many other aspects.
really nice, sir.
Thank you so much, ma'am.
And I
Dr.
must
Dr.
what is
Maulik,
it?
Yes, sir.
Yes.
I want help in future also. And
Okay,
I
sure,
to
sir.
attend such seminar. Your
Sure.
presentation is very good. It is really helpful. I think students are most benefited from this.
Thank you, sir. Thank you so much. Thank you so much. My pleasure.
So thank you, everybody.
Thank you. Thank you.
Okay.
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 Thank you.